So it's called Completeness in Abstract Interpretation, and this is only a personal point of view. So first, what is completeness? Completeness, and you think about logic and incompleteness theorems and so on, is the power of a proof system to prove things, right? So X is complex for Y if X can prove all the things that are true in Y. It's classical definition. And in abstract interpretation, you could transfer the definition. I mean, it's the power of an abstraction to prove a property, or the power of some abstract analysis to prove a property. This seems natural. Now, when I said in the title that it's a personal point of view, is that I didn't plan to do research in completeness in abstract interpretation in the first place. I mean, there are several people in the audience that are more experts than I am in this field. So I got it by accident, and I will explain how. So let us first start with a simple example of an analysis that doesn't lose any kind of precision. And this is the usual example that by Patrick, casting out nines, something that we used to learn in elementary school in France. If all your operations are things like plus, minus, multiply, and you wish to prove an equality modulo n in the end, then you can abstract everything modulo n at every point, and you have no loss of precision. You would not get anything better by running the computation with exact integer numbers and then taking the modulo at the end. You don't get anything better than doing the modulo at every step, which of course requires fewer bits. So that's a very good kind of abstraction. And you could think that this does not happen for real-life static analysis, this kind of stuff. But if you consider the problem now of analyzing caches, the static analysis of cache accesses in programs, and you consider the least recently used cache eviction policy, which means that you have a cache that contains n blocks, and if you have to move out a block out of the cache to evict a block, when inserting one that is not already in the cache, you take the one that was accessed least recently. There are other kinds of policies, and the other kind of policies have bad properties. I have papers on that if you are interested. So, if you would like to do a naive brute force analysis of that, you would collect all the cache states. You would model check this system. And Patrick makes a face, and he thinks it's costly, and indeed, we tried it, it's costly. Now, if you look at it more carefully, what matters in this kind of analysis is you have the last access to A, you are testing whether a new access to A is in the cache or not, and what matters is the distinct blocks that you accessed in the path from the previous access to the current access. What matters is not actually the sequence in this exact ordering, it's just the set of blocks distinct from A that were accessed on this path. The ordering in which you access them does not matter. If you access the same block twice, it does not matter. So you can immediately simplify your analysis by not collecting actual cache states, but just collecting this set of distinct blocks. This doesn't lose any kind of precision. But it's even better, because you would need to collect all these sets of distinct cache blocks. But you don't need to collect all of them. You need to collect only the minimal and maximal elements with respect to inclusion orderings. Because the kind of property that we're looking for does there exist a sequence of lengths greater than n, or there exists a sequence of lengths less than n, and you don't get more precision if you keep elements that are not minimal or maximal. So you see, we have a practical example of an abstraction that doesn't abstract, well, with respect to the properties that we actually need. Now, I should point out that it's not only a question of the abstract domain that you're using, it's also you implement your transfer functions. I mean, you could have a very precise abstract domain, but you could implement some of your transfer functions in an imprecise way. Or you may have a nice abstract domain, and you may use fixed point iterations, and your fixed point iterations may lose some precision. This is well known. And then I was wondering what could be the completeness, not of the domain, but about the analysis. And the definition would be if a suitable inductive invariant exists in the abstract domain, then the analysis will find it. Suitable meaning that you can prove the property that you want using it. And so you could say that an analysis method is complete for an abstract domain if it finds, or at least decides, the existence of an inductive invariant in the abstract domain for any transition system in a class of transition system and any safety property in a class of safety property. That would be a definition of completeness. And indeed, there are many analyses that are complete with this definition. Any analysis that computes the least fixed point of the system and compares it to the safety property, if this analysis can really compute the least fixed point, it satisfies this condition. So examples include fixed point iterations in a domain with ascending chain condition, etc. The ascending policy iteration proposed by Helmut Seidel, and Thomas Gorlitza, etc., etc. You can also, from a more theoretical point of view, if you can define the least inductive invariant using a quantified formula, I mean, that's easy. You just write the definition of what it means to be minimal, and you write that it's inductive using quantifiers. And you're in a theory that admits quantifier elimination, then the least inductive invariant is definable, etc., etc. So you see that you can get complete analysis for real intervals, real octagons, template real polyhedra, and more generally any kind of template domain, because you can always write this kind of quantified formulas. I'm not saying that this is efficient, but at least that exists. You can do it perhaps in a non-practical way. But think about convex polyhedra, the general ones, the ones in which you don't fix in advance the number of faces in the polyhedron that you have. So it's not a fixed template. And if you read the papers, they say they introduce a widening operator, and this is necessary for convergence. So I was thinking maybe I could prove before the 40th anniversary of these papers that there is no procedure for deciding the existence of a polyhedral invariant in that domain. And I sort of failed because I could prove it, but only by using a nonlinear guard. I wanted to prove it with only linear operations. And so the proof sketch is that basically you see the use of polyhedra does periodically some kind of convex Hull operation in use states, but I encode the state of a quantum machine on some coordinates, and the two first coordinates do a parabola. And if you use the nonlinear guard, I'm on the parabola, the only states that remain are truly the reachable states of the quantum machines, and the states that are added by the convex Hull operations are in the middle and are excluded by the parabola. So sort of I was cheating, okay? And then to my surprise, Fijalkov and others called that the Monniaux problem, and they tried to prove that it was impossible to do it with the polyhedra, but it couldn't do it either. So for instance, if you have disjunctions, then they have proved that in certain domains with disjunction it is impossible to do. So this is, I think, a kind of interesting theoretical problem. How do you prove that the existence of inductive invariants in the convex polyhedra, integer polyhedra, real polyhedra, it could be probably different, is undecidable? I don't know how to do it. Or maybe it's decidable, I don't know. So something else that I went into after that are questions of relative completeness. So things like my original problem is an inductive invariant in a certain domain, and equivalent to a second problem is an inductive invariant. And I'm not saying that I can compute the invariant in the second problem, just do transformation. And can I do, for instance, a transformation that solves a problem in the original problem inside a certain abstract domain? And so we went into some the consideration of maps or arrays. So when I mean maps, it's just general maps from X to Y. Arrays are when X is a range of integers. So this was the PhD work by Julien Brel. And so the abstract domain is a kind of template in which you fix for all a certain number of indices, and then you're looking for a property that will link the indices to the values. And you specify inductiveness and safety conditions in this abstract domain. You end up with inductiveness conditions that contains lots of quantifiers, and they do not fit the format of own clauses that you would expect they would do. But you can actually instantiate these quantifiers using finite instantiations, and then you can show that under some syntactic restrictions on the class of own clauses that you're considering, which is just the case, for instance, for transition systems, then you can show that there is equivalence, that this instantiation is complete. And so, to conclude, my research directions with respect to completeness, I mean, if I had time to work on that, I think it's an important question. Which abstract domains truly need heuristics such as widening in order to find solution, and for which we could have some kind of decision procedure? As I said, I failed already for polyhedra to find that. And also, some interesting thing about the work on arrays is that when you have this kind of relative completeness properties, it allows pinpointing when you actually lose precision in a kind of sequence of abstraction. Whereas previous work on this array tend to be some kind of monolithic abstraction and at solving procedure at the same time. Thank you.
Thank you so much for your talk. There are questions?
So you told us that you failed when you tried to prove decidability or undecidability for the Monniaux problem in the linear case. Mm-hmm. Can you tell us what was the main problem that you found in that attempt? If you remember, maybe.
Okay, so...
Or the main challenge which is still there.
So I was trying to prove undecidability, and so I was trying to encode something that was Turing complete into my problem. Then I thought, you know, that there are undecidable problems that are less than Turing complete, but these are pretty artificial problems that I would not know how to handle anyway. So in order to encode some kind of Turing complete state, the thing about the parabola is really nice because you can actually encode the states on the boundary of the polyhedron. Yeah. But I don't know how to encode, how to get away from this nonlinear guard. I tried doing some things in which I would be using integer polyhedra, and I would be sort of encoding the things with the integer points. But then I needed the things like, does there exist a family of polyhedra that have whose only integer points are at the boundary and there are enough of them, etc. And this did not work either. So
we can tell him that we try to generalize your proof. We free guys.
You also failed.
Yeah.
Exactly.
We spent 2 weeks trying.
2 weeks in New York.
2 weeks in New York as 2 weeks.
Okay. Any other question?
Any other question? Okay, so thanks again. No? There is one? I'm sorry, Patrick.
Yeah, it's a bit independent of what they said. You don't mention the concrete property that you use. That is, I was wondering if you may have a completeness, for example, for reachability, but not for traces because tracers would be more precise.
Oh, yes, I forgot to say, it was just for reachability, simple safety properties here.
Okay, okay. Oh, it was a trivial question with a trivial answer, but...
Any other? No? So thanks again, David.